Hi, I'm Olivia, everyone's favorite math teacher, and in this video, we're going to look at, is it possible for us to apply differentiation to equations when we can't necessarily write them as functions? I'm not going to bury the lead on you here. You absolutely can just take the derivative of an equation like we do things with, say, for example, multiplying an equation by a value, taking the logarithm of an equation, exponentiating an equation, and so on. We just simply use the differential operator. And as long as we're following our rules that we've learned so far, we won't have any problem doing this. We do have to learn something, though, in order to do this, which is what we call implicit differentiation. This is where, when we take our derivatives, we always take the derivative with respect to whatever is in the bottom of the operator. So for example, here I have d dx. So when I take the derivative of my equation, again, this is not a function, this is an equation because of the way it's written. When I take the derivative of this equation, I'm treating y as a function of x. It is implied that the y will be replaced with a function of x. This is why it's implicit differentiation. Now, the reason it's like that is because the idea is that, for example, with this circle, I easily could take this equation and break it up into two functions that would define this shape. I would have a function across the top and a function across the bottom. And there are many examples of curves and graphs within algebra and just within mathematics where we could potentially do this. But there are also examples of curves and shapes within all kinds of mathematics where we can't necessarily do this algebraically. And this is where implicit differentiation really comes into its own strength. So I'm going to demonstrate it obviously with this circle because this is one where we can examine it algebraically. But we're also going to look at a few examples where you can't necessarily do it algebraically, but the methods still work. Okay? Now, to do this, we simply take our differential operator and we apply it to the entire equation. When we do this, we're going to take the derivative of each term just like we do before. If the term has an x in it, we just take the derivative. If the term is a constant term, again, we just take the derivative. Any term where we run into the implicit parts, that's where we have to consider, okay, this includes an unknown function or a function where we can't directly take the derivative and we're simply going to write it as the derivative of that function, okay? But we do have to consider that there is something there. And so we're going to be applying the chain rule in order to do this. And so when I do this, I use a bit of a notational trick where I write out the chain rule and then I will write it, the chain rule, as dv over du times du over dx, okay? And the reason I do this is because if I use the normal y over d or dy over du over dx, then what happens is when I write out my two function bits, I get y equals u, I would get, in this case, y equals u squared, and then u equals y, which is a bit recursive and confusing. So instead, I simply write it this way to go, I'm going to take the derivative of the function v with respect to u, so that's my u squared, and then I'm going to take the derivative of the u with respect to x. But I don't know what u is because there's no x involved, so that's just going to stay that derivative, okay? And then when I'm done taking all my derivatives, I'm going to replace all the u's with y's. Simple as that, okay? And so when I do this, here's what happens. Because I'm taking the derivative of v with respect to u, and there is a u here, I can take that derivative normally. That just becomes 2u, which is just the derivative. Now, I take the derivative of u with respect to x. There are no x's here, there are no constants here, so I don't know what that is. I'm just going to say, well, that's the derivative of u with respect to x. I don't know what it is. It's the derivative. And if I ever did know what it is, I'll replace it with that derivative. So I'm just going to leave it as this is the derivative. In Lagrange notation, we would write it with the little prime symbol. So I would write u prime or something like that, okay? This is a very common thing that we do, especially when we get to the part where we're doing integrations. You'll see that, okay? So then when I write it out and I've replaced my u's with y's, what I get is 2x plus 2y times the derivative of y, don't know what it is equal to 0. And then the last step here is I simply solve for my derivative of y. And when I do that, I get that my derivative of y is equal to negative x over y. What this tells me is that my tangent at any point on the circle is right there. So, for example, if I went to the point 3, 4, this is a circle with radius 5, so we know that it'll fit the Pythagorean theorem, 3, 4, 5 triangle. So if I were to go to 3, 4, 3, 4, okay, my slope would be, I put in 3 for x and 4 for y, so it would be negative 3 over 4, meaning that I'm expecting it to be a slope that is less than 1, but also negative. About right there. Yeah, seems to track. It's a negative slope. It's less than 1 because it's not a 45 degree, right? And you'll see how if you check it yourself, it goes around and it exactly tracks what the tangent is at every point on this circle. Now, if we wanted to write this as a function, we absolutely could if we can write y as a function of x. And this is why it's implicit differentiation, is because we're implying that y is a function of x and that we absolutely would write y as a function of x if we could, but maybe it's just a little too tricky, or maybe I'm a little too lazy, or whatever. In this situation, we absolutely can. But again, we end up getting two functions, so if I wanted to write this, I would still have to write this as two functions, because I would need the function for the top and the function for the bottom, and I would still need to know where it is if I wanted to write this in function notation. So the benefit to this implicit differentiation is that I'm not writing this as a function, I'm implying that y could be a function of x. And so I can leave it in this kind of a format unless I needed to write it specifically in that way, okay? And again, the advantage here is that just like we use the chain rule, because there are certain types of functions that we can't solve algebraically, and so things like the chain rule help us with those transcendental functions and things like that. In this situation, implicit differentiation helps us with equations that are absolutely great equations and that we use for a lot of situations, but that we cannot necessarily write as functions, but we still want to be able to take the derivative. Let's look at a few more complicated examples and get some practice. So if you look at this equation, you can tell this is not a function. And I would say you would be very hard-pressed to try to use algebra to convert this into any number of functions via a piecewise function. And if you go look at the graph of this, it's really cool, and you can probably see why it would be difficult. In fact, I implore you to go look at the graph of this. Put it into Desmos or your graphing calculator. But if you were asked to find the tangent to this graph at a point, using implicit differentiation, you would be able to do that. So go ahead and try that now. Apply implicit differentiation to this equation. And I'm going to show you the answer in 3, 2, 1. So I didn't show explicitly what I did for each of the sections, but I did demonstrate the rules that we used, okay? Now, as you can see, what we did, we went ahead and we used the differential operator. And then on the first part, because they contained no x, that's just the chain rule. On the second part, we did have an x, and so we had to use the product rule because we had a term with an x and then a term without an x. So product rule here, and then the chain rule on the part without the x. And then we just had a constant here. And then on the next part, we had to use product rule, chain rule again. And when we do that, we come down here. our basic chain rule gets us this part and then that part. And then our product rule, you can see that what we did was we took our f of x times our g of x, and then the g of x being the y cubed. So we take the derivative of the first part, which becomes the 3y squared, and then the derivative of the inside, so the derivative of y, which is just the derivative of y, and then so on and so forth throughout the entire thing. Now down here you'll notice that I went ahead because writing dy dx became a little bit problematic with my chalk. I went ahead and switched over to the Lagrange notation at this point just for the ease of writing, and that's typically what you'll see when people start using the Lagrange notation. Is once they're done with the operator portion of it, they'll usually switch back down to the Lagrange notation. And that's because the Lagrange notation isn't necessarily as good for using it as the operator indicator. But after you're done with the operator, it's good for notating where your derivative is. Just because it can be a little bit more clear. It's kind of like whenever we're doing transformations and we're marking our image versus our pre-image and we just use the tick mark. It's similar here. It makes it nice, okay? Because then we can simply use it in the same way that we would use any other variable or any other thing like that. And in this case, that's what we did. So we gathered up our like terms, basically our things that had that derivative section, and we moved it over to here, and then we simply factored out the derivative, and then we divided the rest of it over, and we get that our derivative of y is equal to this. So this would be our tangent at any point. And now it's still very complicated, but this does allow us to see what the derivative of a point on that graph would be. And from looking at this, you can tell that, yeah, it's a pretty complicated situation, and there's still going to be rather complicated areas where we may not have a derivative, because there's going to be sections where this thing might still be undefined. We would have to do some more examination on this. And in fact, in later sections in your class, you're probably going to see parts where you're going to look at how do we examine graphs using first, second, third derivatives in order to tell what's happening at the graph, what kind of expectations do we have, and what kind of information can we get, which are just kind of further developments that came as calculus was refined as a study. So let's look at one more example using some of our transcendental functions, and then I'll leave you with a few exercises to try on your own. So this one looks really simple, and for the most part it is. But, well, you'll see. Give it a try, and here's the answer in 3, 2, 1. Now, I did warn you a couple of videos ago that sometimes problems got a lot more complicated than they started out, especially when we're working with transcendental functions. And here's a great example. This is one of the reasons why you want to make sure you organize your work very well, so that you can go back through and just double check that your algebra is good and that your differentiations were done well. So we're going to walk through this one. It actually isn't necessarily as bad as it looks. It just does get a little bit wide and will have a tendency to get away from you if you aren't organized, okay? So I knew this one was going to be rough as soon as I saw that tangent because, again, transcendental functions, if there's not a way to cancel things out, they're going to get a little bit wacky, okay? Now, here we know we're going to have to do the chain rule because anytime we've got something inside a trigonometric function, we're not going to be able to get rid of this part, so we're going to have to do something there. And then on this side, we've got a fraction, which means quotient rule. So here we apply our chain rule, and we take the derivative of tangent, which is secant squared. We take the derivative of the inside, which luckily here, the derivative of x is simply 1. And then because we don't have anything attached to the y, when we take the derivative of y, we just get y prime. Now, again, I am mixing my notation a little bit, but that's because, as you can see, this gets a little bit wild, and the less confusingness that I can have in here, the better, okay? And again, that's where Lagrange notation helps out. So we come through to this side, and we simply apply our quotient rule, and if you remember, the quotient rule is my numerator the derivative of my numerator times my denominator minus the numerator times the derivative of my denominator over my denominator squared. Then I just go through a whole lot of algebra. Now, some people would take it to, I would say, maybe this point or this point, and then divide it here. You do need to get to at least this point where you can get your y prime away. This step is absolutely necessary. Now, I typically will simplify my fractions down because I don't like having addition and subtraction in there. I like to have them as fractions to simplify it into a single unit. Some places they won't do that and they'll keep it as multiple fractions or they'll keep it as multiple operations. There will be a lot of equivalencies, and there you might have a different answer or one that looks a little different than this. Simply take yours and see if it's possible, see if you can make it into one that looks like this, or see if you can make mine look like yours. Via algebra, you should be able to modify them into each other. If you don't, drop into the comments and see if I made a mistake, or if yours looks significantly different, put it in there and I'll be happy to check it out and see where maybe there might have been a mistake either on mine or yours. So after this, I'm going to leave you with a couple of exercises to continue practicing, and then we'll do the outro. So I hope that overview of implicit differentiation helped. And in your classes, hopefully up to this point, in addition to learning all of these skills and tools, you've been using them in kind of some basic applications. In the next few videos, we're going to look at some explicit applications that students are expected to know whenever you're looking at things like the AP test or just in general from a calculus course. Because remember, the purpose of calculus was to answer the questions about how we can calculate rates of change whenever algebra wasn't quite sufficient. And then from there, it grew into a bigger science. So remember, if you have any questions, feel free to drop into the comments or join us on Discord. And then the answers to the exercises are going to be at the end of this outro. See you in the next video.